morning, everybody. Today, in this class on, as you can see here, that is differential equation, that is, of course, a series solution. In this class, I am going to recapitulate the previous part of the differential equation which we have already learned, and uh, another process to solve a differential equation with constant coefficients, and even if there exist non-constant coefficient but they are continuous, we can use those tricks to solve the differential equation. We have already learned that the differential equation is a very basic part of mathematical physics, because in almost every cases, in case of classical mechanics, quantum mechanics, and in all the cases, you are using those differential equation, but you are using those differential equation up to a good approximation to make your problem more simpler, for that you can get some solution of that particular differential equation in a much easier way. But the things are not same for all the time, right? There are some special functions. They are called even Legendre polynomial, Hermite polynomial. In those cases, you can see that there exists some non-analytic point of that particular function at which the function is differentiation of that particular function is problematic. So you have to use some different tricks to tackle those problems. So till now, as far as we are get in touch with differential equation, we have learned that most of the cases we are tackling the differential equation as far as we have learned that most of the cases we are using a good approximation method. Okay, to solve this differential equation, and we have not yet paid any attention on the nonlinear differential equation, and we are in this class we are going to discuss the linear differential equation, right? So we are not bothered about the nonlinear cases. We are only dealing with the linear differential equation, because nonlinear is much more difficult to solve. But say, for example, we have used a general form of a differential equation. In this case, we are using that dy d of y that should be equal to f of x. This is the general form of a differential equation, linear differential equation, where this differential operator d might have a second order or a third order depending on the power of this differential equation. So d to the power in y, that might be a function of d. Okay, so d might be a function of the differentiation, that is d to the power some n divided by dx to the power n. But here fx is another function. So in this case, for linear second order differential equation, as far as we have learned, we can write this differential equation in much simpler form, that is in much simpler form, that is d2 y by dx2. Obviously there exists some coefficient here, it is p0x plus p1x dy by dx plus p2x y. This will have upon fx. So this is the general form of this particular second order differential equation, linear differential equation, and these are having in this form. Now for simplification we are going to divide with p0x in both the sides, and we are getting a function such as d2y by dx2 plus rx dy dx plus qxy. This should be f prime x, right? So this is the most general cases of this differential equation. Now this differential equation can have, this particular differential equation can have the solution if and only if this three function, that is rx, qx and f prime x, and f prime x will be a continuous function. Right? So this particular differential equation can have a solution if this three function, that's a function rx, qx and f prime x, will be continuous. And you can see here these three function may be a function of x, may be a constant. So all types of possibilities we are getting into this equation. Okay, so if this rx and qx f prime x, they are constant, so if they are constant, they must be continuous function. There will be no problem with that. But if this three function will be a function of x, then the condition of continuity of function comes to play if we have these three function have solution within some range. Now there exists not only the solution if these three functions are continuous, but also the same solution can be represented as a general solution, or that is y equal to complementary function plus y particular integral, right? So if these three functions rx, qx and f prime x, they are continuous, we can write this function, the solution of this of this differential equation, in terms of yc plus yp, where this yc, we have already learned that this yc is nothing but general solution of a special form of this differential equation, where this f prime x becomes 0, right? So you will get that when d of y is equal to 0. This is the special form of this same differential equation. So these are called complementary function. Right? And this yp plays a very special role, because yp is called particular integral, and this particular integral is nothing but any solution of this particular differential equation dy equal to kx. Okay, so any solution of this particular differential equation is called particular integral. So the general solution is basically the combination of yc and yp. We have already learned these things, but the problem is, as far as we are concerned, how do we get this yc and yp? These are, we have already learned that. So the problem is that how to find out yc and yp. Okay, now it is very easy to find yc because you are making the term dy equal to 0 and you have to choose a trial solution, y equal to e to the power mx or something, and you put there, you get a second order linear equation. By solving that equation, you have got either different values of m, and from different values of m you can have this yc, the value of this yc, right? So finding yc is not a problem, and this yc have different forms depending on form of yc depending on either the roots are same or not, or real or imaginary, right? So this solution of yc, this yc depends on either the roots are same or they are not same, they are real or they are imaginary. Say for example, if roots are not same, then yc can be written as c1 e to the power alpha 1x plus c2 e to the power alpha 2x, where this alpha 1, alpha 2 are real. Okay. Again, if roots are same, then this yc complementary function can be represented as a plus bx e to the power alpha x, where this alpha is real. Okay, so roots are same, and in both cases these roots obviously are real roots. Okay, so previous two cases, if we want to get if we get some solution, then the solution must be real, and of course either the solution are same or not same, right? Now if the roots are imaginary, so in case of imaginary roots, we can write yc as e to the power gamma x times e cos kx plus b sin kx, where this gamma is real but k is imaginary. So in this case you will get that the gamma is real, this gamma is real, but this k, they are the imaginary. So in this process you will get yc. Now you are using the method of undetermined coefficient. You are using the method of undetermined coefficient undetermined coefficient, right, to find out the solution in some special cases where this px qx, they are constant okay, and this fx can have some special values, so special forms. So this undetermined coefficient, in that case px qx must be constant and fx have some special form, and those forms are like e to the power mx or x to the power n or cos kx or sin kx or log x, etc. So if those effects have some special form like this, you can apply the method of undetermined coefficient to get your required solution. Now we are we have already know about the undetermined coefficient, so I'm not spending any time with this. And another part of this differential equation have, that is the method of variational parameter, that is variation of parameters. And using this variation of parameter, we can always find yp if yc is known. Okay, so we can always find yp if the form of yc is known, and we are dealing if we are dealing with constant coefficient where px and where rx and qx fx are either constant, or then the continuity of this three term is automatically resolved. So if they are constant, they are automatically become continuous, so there will be no problem with this. Now we know that in this case, after application of this variational parameter, we are reaching with a solution that of y complementary function yc if this will be a1 psi 1 x plus a2 psi 2 x. If we are reaching with this solution, then we can calculate the value of yp in terms of some special form, that is f1 u1 plus f2 u2. Okay, where provided the two linear equation will be satisfied, that is f1 prime u1 plus f2 prime u2 equal to 0, and f1 prime u1 prime plus f2 prime u2 prime, this will be fx. And the form of this is called, from this we are getting the Wronskian of this differential equation. So variation of parameter is solved, and we can have a good approximate solution if we are dealing with special case of differential equation where these three functions are either the constant or they are continuous, or the form of fx is known. Now, what happened when we have a form of differential equation where we have a form of differential equation where this Rx, Qx, they are the function of x rather than they are constant. Okay. Now, how could you tackle this function when this Rx, Px, they are practically not constant? Till now, we are utilizing some special cases where fx, the form of fx is known, or this Rx and Qx, they are constant. But now we are going to deal with some problem where this Rx and Qx, they are not actually constant, but they are variable, and that particular variation depend on some independent function x. Okay, so in that particular case, we are tackle the general solution of this type of differential equation by applying the power series. Okay, so as far as we know that the form of differential equation, we have already learned that dx square plus rx dy dx plus qx y, this should be fx. And this fx at right hand side, for some special cases, we are dealing with 0, as we are concerned about the complementary function of this solution. Now there is a theorem, and that theorem basically tells that if these two functions, this Rx and Qx, they are analytic, now this term analytic comes, I will come to this term later. Now if these are analytic functions within a range of interval where x minus x0 is less than some xi, then every solution of this particular differential equation of this dy equal to 0 of linear differential equation, this defined as at x equal to x0 is analytic. So, and this function, so we are having a good approximation or good method of this theorem, that if we have a special form of this differential equation like this, and at the same time we are getting two coefficients in such a way that they are analytic. Now, what does this analyticity means? Now, a function analytic means it can be represented as a convergent power series, and this, the differentiation of that function exists at that particular point. Okay, so this is the meaning of this analyticity of a function. Now, if this Rx and Qx are analytic function within this interval, then every solution of that particular linear differential equation defined at this particular point as analytic, and this analyticity of every solution that exists at least within this domain x minus x0 less than xi, right? So this is basically the form of this power series. Now we have already learned that if Rx and Qx are constant, then there will be no problem with the continuity of that particular function. But if this Rx and Qx are constant, I mean continuous, then there always be some general solution. So this is the proposition of this theorem. Okay. Now we are going to we are moving to some step forward and say that except our recapitulation, that not only this function are constant, but if they are continuous, there will be not only we are getting some general solution, and that solution particular solution can be represented as the form of this convergent power series. Okay, so this is the particular case of this differential equation. Now we are dealing this differential equation with some special cases, and let me guess that the solution of the particular differential equation is known to us, and we are using the form of this particular differential equation or the result of this power series to verify that this power series ultimately gives us the same solution as we are getting from the differentiation of that particular solution. Now let me start with a special function, that is a simple harmonic motion, right? Now for a simple harmonic motion, let us consider a SHM. Now, if we are working with a simple harmonic motion, then we know that the form of the simple harmonic motion is m d2y by dx square plus ky. This should be 0. Here we are only using two terms, that is y is a function of position and the x represent time frame. Okay. So we have already know about the solution of this differential equation. So how could you solve this? You will get d2y by dx2 plus ky my. This will be equal to 0. Now assume this k by m as omega square, and you will get the d2y by dx2 plus omega square y. This will be 0. Now from this equation, this is a very simple equation, and you have already know that the solution of this differential equation will be yx, a function of x, that will be a some arbitrary constant cos omega x plus b sine omega x. So we can apply this solution in this form or exponential form by rearranging either this cos function or sine function. For our simplicity, we have assumed that this k by m, or the value of omega equal to 1. Okay, for simplicity of this problem. Now, if omega equal to 1, the form of this differential equation becomes different. So d2y by dx2 plus y, this should be 0. And the solution yx, this will be a cos x plus b sin x. So there will be no problem with this. Now, as we know the form of this differential equation, we are going to apply our power series to solve this particular differential equation. And if that power series provide me a solution, or that particular power series provide me a solution that will be compatible with the exact form of this differential equation, then I'm sure that that power series have some problem, and we can use that power series particularly in all the cases where the form of these two functions, that is either px or qx, they are continuous and they are, although they are not constant. Okay, so let us assume that the power series y, obviously this is particular integral. Now we are using this as y as trial solution by t. Okay, so the trial solution, we are using this as a convergent power series a in x to the power n, right? And now we are going to differentiate this function term by term. How? So if you expand this power series, you will get a1x plus a2x square plus a3x cube such and such, right? Now if you differentiate this yt, you will get that a1 plus 2a2x plus 3a3x square in this way. Okay, and the form of this differential equation can be written as n equal to 1 to infinity, as we are leaving this first term when I am differentiating this whole. So n equal to 1 to infinity a n x to the power n minus 1 into n of x, right? So when you differentiate, you will get this term. Now if you differentiate second time of this power series, what you will get, d2 yt by dx2, this will be obviously, now this term will become 0 and you will get just 2a2 plus 6a3x plus dot dot dot. Now this can be expressed as sum of n equal to 2 to infinity n into n minus 1 a n x to the power n minus 2, right? Now you see that if you start the first term with n equal to 2, then you will have this term at the first. And in this case, if you start with n equal to 1, you will have this term. So starting from n equal to 0 in this particular case, when the first derivative comes in, is not possible. And in this case, when first derivative comes in, is not possible. So n equal to 2 to infinity n into n minus 1. Now what I will do here, I have to substitute this term in that particular differential equation, and we have just make the coefficient of x to the power n same. So we are now using this term as sum over n equal to 2 to infinity n into n minus 1 a n x to the power n minus 2 plus sum of n equal to 0 to infinity a n x to the power n, this will be 0, right? Now, so this is just infinite. Okay, now we will have a problem. What is the problem? In the left hand side, you can see here the coefficient of term a2 exists, but here we are starting with coefficient of a0. So in this series, the series start with coefficient of a2 and this series start with coefficient of 0. But there will be no problem, because if you see here, if you raise this n minus 2 by a factor plus 2, so raise this term, by a factor 2, because this term is within this summation, and due to that raising you have to compensate in this summation here. So compensate by 2, right? So what you will do here, you will raise this term by 2 and you will compensate this term by 2. Now what you will get, if you raise this term by 2, everything, this n will raise by 2. Okay? Now you will get a general case in, and if you compensate it by 2, then just subtract 2 from this n equal to 2. So what you will get? This will be n equal to 0. Now infinity minus 2, that becomes once again infinity. So this will be n plus 2. N will be replaced by n plus 2 into n plus 1 an plus 2 x to the power n. So now it's become x to the power n if you raise it by 2. And of course, these things will say, because we are not raising or compensating any of this power of x to the power n or any of the term that basically gives me the form of this summation. So this remains as it is, n equal to 0 to infinity an x to the power n. Right? So here you will see that this term comes with an plus 2, or the coefficient of x to the power n comes with n plus 2, and this term gives me an. So by applying these things, we are having a very well-being relation between two coefficients, that is an and an plus 2. Okay, so what is the form of this an plus 2 here in terms of an? Now, as the coefficient of x to the power n remains same and almost everything within the sum remains same, so let me write another term. So this can be written as n equal to 0 to infinity n plus 2 into n plus 1 n plus 2 plus an times x to the power n. This will be 0. Okay. Now, for a power series, this is also a power series. So this power series will be 0 if the coefficient of each term will be 0. So the coefficient n plus 2 into n plus 1 an plus 2 plus an equal to 0. So this coefficient of 0 not only provide me the condition of this summation equals to 0, but also it provide me the relation between an and an plus 2 of the solution, right? So from an plus 2 we can write this as minus an divided by n plus 2 n plus 1. Okay, so we are reaching in a very crucial region where we are having a good relation between the coefficients of this power series, that is an plus 2 and an. Now we replace, as this is the sum of this power series, so n runs from 0 to infinity, and as you are putting n equal to 0 here, you are also getting a term a0. So for a good approximation, when I am using that power series, I have to use an approximation that is A0 is not equal to 0. The same proposition goes for A1, that is also not equal to 0. And if this proposition is good and we are taking this to proposition, then we can write this particular equation in terms of this two coefficient. So in terms of two arbitrary coefficient, we can write the whole equation. Now let us try to solve this differential equation, or let us solve this equation. So what we'll get when you are putting n equal to 0, from this equation, what we'll get? A2 is equal to n equal to 0, so minus A0 divided by 2 and 1. Okay. Now if you are putting n equal to 1, what you will get? A3. This will be minus A1. So you are putting n equal to 1, so this will be 3 into 1. 3 into 2, sorry. This will be 3 into 2. Right? Now, if you put n equal to 2 here, you will get A4, and this will be minus A2 divided by 4 into 3. So this will be A0, 4, 3, 2, 1. We are going to replace this term here. Replace A2 from this point to this point. So you will get this term. Now if you put n equal to 3, what you will get? You will get values of A5, that will be minus A3 divided by 5 into 4. So this will be A1 divided by 5, 4, 3, 2. Okay. In a similar way, if you put n equal to 3 here, n equal to 4 here, what you will get? A6, and the value of A6 will be, obviously this is n equal to 4, so this will be A4 times 6 into 5. So you can write this as A0 minus, obviously here, 6, 5, 4, 3, 2, 1. So let us multiply this with 1, nothing will come. So now n equal to 5, A7, and this A7 will be minus A5 times 7 into 6. So this will be minus A1 by 7, 6, 5, 4, 3, 2, 1. Okay, so we are getting lots and lots of terms by putting different values. So in this way, we can calculate all the terms, and now we are using the solution as trial solution as sum over n equal to 0 to infinity a in x to the power n. Now what you will do, you will just expand this series. So this is A1, A0, A1x, A2x squared plus A3x cubed, dot dot dot, and you are going to put all the coefficient here. You will get the things. So what you will get, this will be A0 plus A1x plus A2x squared. So A2 will be nothing but minus A0 by factorial 2. So this will be minus A0 by factorial 2x squared. Now A3x cubed, what is the value of A3? This will be minus A1 by factorial 3 x cubed plus Now this will be a4 x to the power 4. Now a4 here is a0 by factorial 4 x to the power 4 plus what we will get here a5. So this will be a5. So this will be plus a1 by factorial 5 x to the power 5. Now minus this will be a6. So this will be a0 by factorial 6 x to the power 6 minus a1 by factorial 7 x to the power 7 plus 6. Okay, so you are getting term by term and you are putting the value of this term by term, you will get the general solution. Now you have to rearrange this equation to get the particular form of the expected form of this that equation. So what we will get? We will get this y as a0 times 1 minus x squared by factorial 2 plus x to the power 4 by factorial 4 minus x to the power 6 by factorial 6, this plus a1 x plus x cubed by factorial 3 or minus x cubed by factorial 3 plus x to the power 5 by factorial 5 minus x to the power 7 by factorial 7 plus x. So you will get the general form of this differential equation. Now it is clear to us that this two power series is nothing but a series of sine and cosine. We have learned this. So the sine and cosine series what we will get. So this will be, of course, 1 minus x squared by factorial 2 plus x4 by factorial 4 x6 by factorial 6. This is obviously cos of x, and the term x minus x cubed by factorial 3 x 5 by factorial 5, this obviously sine of x. So what we will get? We will get the desired equation a0 cos x plus a1 sin x. Previously, we are dealing with the same problem and we are applying our regular method of undetermined coefficient to determine the solution of this particular differential equation, and we are having the form that is a cos x plus b sin x. Now these two solutions are just equivalent, except these two coefficients, they are the constant. So we are choosing the coefficient according to our choice and we will get the required solution. So power series can provide me a better way of understanding a physical problem, because if you use the power series, you can have some facility in your hand, and those facilities are, first of all, facilities of using power series. First of all, if you use the power series as a solution, you can add this power series term by term, You can subtract also, term by term. So you can add any two power series term by term. You can subtract power series term by term. Second, you can differentiate this power series term by term. And obviously, you can use multiplication if you have more number of solution to cope up in the same frame. So you can multiply power series series. So there will be lots of facility in your hand when you are using the power series of any a power series to solve any differential equation. And ultimately, as I give you some example, that you will see that that particular power series ultimately uh, give us the same solution of that particular differential equation as we are expecting from any differential equation. So use of power series is much powerful for any differential equation when there will be some problem with the differential equation, that we can have not only have a constant Px, constant Rx and Qx. We don't have that constant Rx and Qx, but this Rx and Qx, they are continuous function of x. So ultimately we have learned that this power series can have very special features when either when this Rx and Qx, they are constants or they were continuous function of x. So if they are constant, we are using our regular method as we have discussed in earlier case, and in the rest of the part, as I am discussing with the function of x in our next class, I will discuss the use of that power series when those two functions fx and qx, they are some function of x, right? So till then it is fine. Thank you.